up, everyone? Let's talk about multivariate analysis of variance problem this week. Researcher hypothesizes that people who struggle with test taking do so primarily due to their higher levels of generalized anxiety rather than their anxiety that is specific to test situations. However, it turns out that generalized anxiety and test-specific anxiety are correlated. So those with higher general anxiety also tend to report higher test-specific anxiety. But the hypothesis here is that really it's a generalized anxiety that causes the difference between good and bad test takers, right? So in this particular study, they've got 30 good and 30 bad test takers. That's a variable called test taker, and they're coded 1 and 2. Their scores on measures of generalized anxiety and test-specific anxiety are provided below. Higher values always indicate more anxiety of both types. And your job is to test the following research hypothesis. Is it generalized anxiety or test-specific anxiety that best differentiates bad test takers from good test takers? So in this case, the researcher thinks that generalized anxiety is really the cause, so that is their primary dependent variable, and test-taking anxiety is a secondary dependent variable. So let's get to the question. So what is the one independent variable in the study? Well, that independent variable in this case is the test taker type, this variable right here. And then what are the two dependent variables in the study? Generalized anxiety and test-taking anxiety. So we have the situation here where you have a single independent variable, but two dependent variables. So the researcher hypothesizes that individuals who struggle with test taking do so primarily due to higher levels of generalized anxiety rather than anxiety specific to test situations. So which dependent variable should be considered primary? Well, they think generalized anxiety is the important DV, right? So generalized anxiety is the primary dependent variable, and test specific or test anxiety is a secondary dependent variable. So step one is to run some preliminary correlations. So let's go ahead and do that over in SPSS. Go down to correlate and bivariate. And we're just going to throw these guys over to the right. That's the IV and both DVs. Make sure you got two-tailed. And I click this to show only the lower triangle. And there's our correlations right there. So we got a correlation between generalized anxiety and test taker type, test taker anxiety and test taker type, and then test taking anxiety and generalized anxiety. Those are the three correlations we want. So remember, when you have a dichotomous variable, it's a little difficult sometimes to interpret, like test taker type, what's higher and lower. So up here on the left, note that test taker type 1 equals bad, 2 equals good. 1's bad, 2's good. You can only have one of two values. So a lower value on test taker type means bad test taker. A higher value on test taker type means you're a 2, you're a good test taker. All right, let's try to interpret these. Here's our correlation decision rules. There's our correlations. So between generalized anxiety and test taker type, it's negative 0.35. Rounded that, it gets a star. Between test taking anxiety and test taker type, that's this guy right here, is also negative 0.35 with a star. And then finally, between test taking anxiety and variable 2, which is generalized anxiety, it's 0.64 positive, gets a star. So negative 0.35, negative 0.35 is a little weird that they're both rounded the same number, but they both share about the same relationship with test taker type. And then there's a big overlap, right, between the two types of anxiety. 0.64 is a fairly big correlation. All right, so let's interpret the meaning of each correlation below. So test taker type and generalized anxiety. So generalized anxiety, test taker types right there. It's negative 0.346, which we rounded to negative 0.35. So that means as this goes up, because it's going to be a negative correlation, this one goes down, right? This goes up, this goes down. What is down on test taker type? Going back, remember, test taker type is a 2-level variable. You can be a 1, you can be a 2. Those are your only choices. A lower value means that you're a 1 or a bad test taker. So as generalized anxiety goes up, test taker type goes down to bad test taker, which is a Roundabout way of saying bad test takers tend to have higher generalized anxiety. So there's also a negative correlation between test taking anxiety, which is the next one, and test taker type, right? So as this goes up, this goes down. What's down on test taker type again? Well, that's bad test taker. It's being a 1, not a 2, right? So again, looking here, going down on test taker type means you're a 1. So going up on this, it's negative, is associated with going down on this. Bad test takers also tended to have higher test-specific anxiety. All right, and finally, how about generalized anxiety with test-taking anxiety? That's right here. This guy, positive 0.64, so as one goes up, the other one tends to go up. This tells you that people who tend to have higher going up on test taker anxiety also tended to be higher on generalized anxiety. So a positive relationship. One goes up, the other goes up. 0.64 is the correlation for that. So do bad test takers seem to be higher than good test takers on both types of anxiety? Yes, bad test takers were higher on both, right? We determined that. Consistent with the hypothesis, yes. Bad test takers tend to have both higher generalized anxiety and test-specific anxiety. And then what percentage of overlap between test-taking anxiety, what is the percentage of overlap between test-taking anxiety and generalized anxiety? Well, I'm asking you there for R squared. So you literally take your 0.64, which we'll do 0.64, and we'll square it. You get 0.4096, so about 0.41. That's a proportion. I tell you to multiply it by 100 to get the percentage. That's 41%. So there's about 41% overlap between generalized anxiety and test-specific anxiety. So pretty big overlap between those two variables. All right, so we've established that those DVs are correlated. Let's go forward and do our actual multivariate analysis of variance. So that's under Analyze and General Linear Model in Multivariate. Our dependent variables, in this case, we have 2 of them, generalized anxiety and test-taking anxiety. Fixed factor is the name for independent variable in this analysis, so we'll click test taker type under there. Under plots, I tell you to go ahead and put test taker type on the horizontal axis, click add, and select bar chart for that. So you get a bar chart for those guys. And then under options, I tell you to get descriptive statistics, homogeneity tests, and estimates of effect size. All right, that's it. Click the OK button. And this is going to analyze whether these 2 things combined differ for the groups defined by test taker type, good and bad test takers. All right, here's our, oops, too far. Here's our output or our MANOVA. So in our MANOVA, the first thing we start out with is a bunch of means, and we get a box test of equality of covariance matrices. We get a multivariate test. We get Levine's test for each of the DVs individually, and then we get univariate ANOVAs also printed. At the bottom, you get some plots. So let's answer some questions. First of all, let's get some means and standard deviations for generalized anxiety. Generalized anxiety, bad test takers, 11.03 is the mean. Standard deviation is 1.43. For good test takers, so sorry, that's these guys right here. For good test takers, our means there are 10.07 and a standard deviation of 1.23. For test-specific anxiety, that is 11.6 and 1.67 right there. And then for our good test takers, we've got 10.5 mean with a standard deviation of 1.31. You round it 2 decimals. So next we're going to check the homogeneity of covariance matrices assumption for MANOVA. We're going to use this box test to do that. And basically using alpha of 0.05, do the data appear to meet the homogeneity of covariance matrices assumption? Another way of saying, is the box's test of equality of variances sig greater than 0.05? 0.097 is our sig for our boxes, and that is indeed greater than 0.05. So we would not be rejecting the null here, which is that there is a difference among the covariance matrices. In normal person language, when this thing is not significant, it means you met the assumption. So we would say, yes, we met that assumption. So the next one is based on the results Box's test of equality of covariance matrices tells us we met the assumptions, the number of levels of the independent variable, the relative sample sizes, which of the four multivariate statistical tests in here. So you got Pillai's, Wilks, Hotelling's, and Roy's largest root. Which test is most appropriate to interpret your MANOVA? So for this, you want to go to the lecture from this week. This particular slide 8, tells you when to pick which of the different multivariate tests to interpret your MANOVA. So Wilks lambda, it's good when the assumptions are met, sample sizes are equal. That is the case here. Box M is, avoid it when box M is significant. It's most the commonly reported one because it's first on the list, but it is sensitive to violations. Pillai's you can use when box M is significant, so you violated those assumptions. Or your dependent variables are really highly correlated with each other. So really big correlations. Well, we haven't violated the assumptions, right? So use this basically when violations occur. Hotelling's trace, or T squared, is when you've got a MANOVA that just has two groups for the independent variable. You don't want to use it if you have more than two groups. It is sort of like the t-test equivalent of Wilks lambda, essentially. So if you got a two-group design, two levels of the independent variable, this is the one to use. And then finally, Roy's largest root is the one to use when you have one dependent variable that totally dominates the relationship between the two. And so it's meant to focus on the strongest single effect. It's kind of rarely used. I've never seen, the only two I've ever seen used are Wilks and Hotelling's, to be honest with you. And Pillai's occasionally if things are, you violate those assumptions. So what's the most appropriate one in our case? Well, we got a two-level independent variable. We got we did not violate the assumptions. And we have basically equal sample sizes in the groups, right? 30 and 30. So I would say Hotelling's trace is probably your best choice. So Hotelling's trace would be the choice that I would pick. Excuse me. Gotta be honest with you, most of the time it doesn't really matter. So if we look at the actual output, you'll see that every single one of the tests is statistically significant. So it doesn't really matter which one you pick, but the most appropriate one is Hotelling's trace right here. So Hotelling's trace is the answer to 10. Based on the table called multivariate test, this table, and Hotelling's trace. So I literally tell you which one I want you to use here. Do the good and bad test takers differ on combined generalized and test taking anxiety? So this test right here for Hotelling's trace for test taker type tells you, do the good and bad test takers differ from each other on combined generalized plus test specific anxiety, these overlapping DVs? And because sig here is less than 0.05, the answer is yes. The combined DV differs between those who are good and bad test takers. Cool. So we got to write that up. So the way to do that is Hotelling's trace, or T squared, you could use here if you wanted, is equal to 0.07 or 0.17. That is approximately equivalent to an F. That is 2 in 57 degrees of freedom, F value of 4.93, and our P is less than 0.05. No need to do your partial eta here. So that's where all that came from. All right, so good and bad test takers differ on combined generalized and test taking anxiety. But remember, the hypothesis here is that really the big difference between good and bad test takers is their general anxiety, not their test specific anxiety, right? So in this case, we're going to do a step-down analysis where we first look at whether they differ on generalized anxiety, and then we'll see, second step, if they differ on test-specific anxiety after adjusting, like ANCOVA, basically. If we adjust for differences in their generalized anxiety, we take that out. Do they still differ on test-specific anxiety? That's how we test this researcher's hypothesis. So first, let's look at our Levine's test of homogeneity of error variances, and based on the based on mean row, do we violate the assumption for either generalized anxiety or test taking specific anxiety? Neither of these sig values are less than 0.05, so it looks like for both of the dependent variables, we've met the assumption of homogeneity of variances. So that again, the answer therefore is, or the question is, Check it using, do the data appear to meet the homogeneity variances assumption? Yes, they do, because neither sig is less than 0.05. All right. So Bonferroni corrected alpha level. So because we're going to be doing multiple tests here, we need to account for type 1 error inflation. And in order to do that, we do something called a Bonferroni correction or Bonferroni corrected alpha level, in which if we want to maintain a 0.05 alpha level, we need to divide by the number of tests we're doing. So going back to our handy dandy calculator, we want to maintain an alpha level of 0.05. We have two dependent variables that we're going to be doing separate tests on. So divided by 2, you get a new corrected alpha level of 0.025. So each test we evaluate at 0.025 instead of 0.05. That makes sense. So that is our Bonferroni corrected alpha level. It has to be P has to be, or sig has to be less than 0.025 for each of the tests for us to conclude that test is statistically significant. There's a difference between the groups. All right, so let's go to our test of between subjects effects table, this big old monster. In here, there's a bunch of stuff. We don't really care about corrected model, intercept, total and corrected total may or may not be correct. Usually, I don't trust them, so I tell you guys to add up your own sum of squares and degrees of freedom. But there is test taker type is useful, and so is error. So under test taker type and error, note that there's 2 rows. There's generalized anxiety and test anxiety for those, right? This generalized anxiety row is our first step down tests. So we want to look at the row for the independent variable, test taker type, that's these rows. And then for our primary dependent variable, which is generalized anxiety, and using our Bonferroni corrected alpha level, we want to see is our sig less than 0.025. Now, this test right here is just a straight up ANOVA, basically. It can, which is kind of like a t-test actually, but we're using ANOVA in this case. It tells us, does generalized anxiety differ between the test taker type groups, good and bad test takers? Sig's less than 0.025, our Bonferroni corrected alpha level, so we would conclude, yes, indeed, there is a difference between our test taker groups and generalized anxiety. What is that difference? Well, let's go look at the means. So for generalized anxiety, bad test takers had a mean of 11.03. Good test takers had a mean of 10.07. This difference of about 1 is statistically significant, meaning bad test takers had higher generalized anxiety than good test takers. That is what this test tells us. Incidentally, and peeking ahead, well, actually, let's not do that. So why or why not? Well, the simple answer of why we would conclude that bad and good test takers differ on generalized anxiety is that our sig value here is less than 0.025. That's the simple and shortest version. We want to calculate our proportion of remaining variability. So the couple ways to do that. It turns out in this case, the eta squared is actually correct. The actual formula for it is the sum of squares for the IV divided by the sum of squares of the IV plus error. So the harder way to do it would be to take that sum of squares and divide it by that sum of squares plus that sum of squares. That's what we're going to do real quick. So on the bottom here, we need to get our sum of squares IV plus sum of squares error. So that's 14.017 plus error of 102.833. That's 116.85. We need to divide 14.017 by 116.85. Was that 116.85? It was. And that's equal to 0.1199. That's going to round to 0.12. And that is indeed the partial eta squared that it gave us. So the answer for number 16 is 0.12. Easy way to get it was look here. The harder way was to go through that calculation. So we need to fill out our F value. Our F value is an F of 1 in 58 degrees of freedom is equal to 7.91. Our P Our sig was less than 0.025. Remember to use the bond formula corrected alpha level, as it says here. And then our eta squared is equal to 0.12. And that's where we fill all this stuff out from. So what's it mean? Well, we know that this tells us that this ANOVA test here tells us that the test taker types differ on generalized anxiety. And when we looked at the means, we saw that specifically bad test takers have higher generalized anxiety than good test takers. That's what it means. All right. That's for number 18. The next step in our step-down analysis is actually to do an ANCOVA. So we know that good and bad test takers differ on generalized anxiety. Cool. Remember, the hypothesis was that really generalized anxiety is what makes the difference between good and bad test takers. So if we adjust for this, we won't find differences on test-specific anxiety. So to do that, that should sound like ANCOVA to you, and that's indeed what we're going to do for our next step. We're going to do an analysis of covariance. So where we analyze the second DV, test-taking anxiety, and adjust for the primary DV, generalized anxiety. So we remove differences in generalized anxiety. So I can go to general linear model and univariate. Our dependent variable in this case is that secondary DV. We want to know if they differ on this after we adjust for this. So generalized anxiety is our covariate. Test-taking anxiety is our dependent variable. And test taker is our fixed factor. So we want to get some plot, our A plot. So we're going to put test taker type on the horizontal axis. And then I tell you to click add and make it a bar chart. And then scooting on down. Remember when you do analysis covariance, you have to get the covariate adjusted means. That's under E means. Move test taker type over to the box on the right. It'll get you covariate adjusted means for the test taker type groups. And then under options, I'm guessing we want to get the usual three things. Yeah, descriptives, homogeneities, and estimates of effect size. Continue, and okay to run our ANCOVA. And it threw it way over there again. There it is. So this is actually our ANCOVA. ANCOVA. And up here is our MANOVA. And just so I don't get confused, let's go ahead and do that. All right, scooting on down to our analysis of covariance. Let's see what our questions are. So first thing is we got to get our means and standard deviations. So let's go ahead and get those. So our means for bad, and again, the DV here is test taking anxiety. And remember, you've got unadjusted and adjusted means. So you got crude and adjusted means. So these are the raw means, differences in test taking anxiety between good, bad, and good test takers. This is after you take out variation in those means that can be accounted for by the generalized anxiety of bad and good test takers. What are those means? That's what we want to fill in. So the raw means are up here in our descriptive statistics. So for bad test takers, we've got a mean test taking anxiety of 11.6, standard deviation of 1.67. For our good test takers, we've got a mean of 10.5 and a standard deviation of 1.31. So that's this first row right here, coming from these right here. Our adjusted means come from a different table. They come from estimated marginal means down here. These are our covariate adjusted means. So 11.28 is our, right here is our bad test takers covariate adjusted. So it went from 11.6 to 11.28. It went down a little bit. Our mean for good test takers is 10.82 right there. And so the mean for good test takers actually went up a little bit, right? So they're kind of meeting in the middle maybe. Now, to get the standard deviations, it's a little tricky. So SPSS gives you the standard errors. We need standard deviations for APA format. And in order to get that, you got to do this little formula. Standard deviation is equal to a standard error times the square root of n. So it's not too bad. So the n's in this case for each group were 30 and 30, 30 and 30. So we need the square root of 30, and we're going to multiply it by standard error. Note that it's the same standard error for both groups. So this is going to be one calculation to get the standard deviation for both groups. So 30, again, is the n. We need the square root of that. It's this number right here. And we need to multiply that by the standard error, either one, it's the same number, 0.231. And that gives you 1.265, which would round to 1.27. And because the standard error is the same for both groups, the standard deviation is 1.27, 1.27 for bad and good test takers. All right. That's, I think, the hardest part, honestly. All right, so we've got to fill in our ANCOVA, summary table down here. Generalized anxiety was our covariate, test taker type was our IV. We need our error, and we got to get our totals. So this is one of those cases where you can see what I filled in doesn't match total or corrected total. So you really do need to hand calculate this stuff, add up your sum of squares total and your degrees of freedom total. So generalized anxiety, sum of squares is 45.50, 1 degree of freedom, mean square is 45.50, F value is 30.44, right there. It gets a star. Why does it get a star? Because the generalized anxiety is evaluated at 0.05, right? The original alpha level, because it's not the other dependent variable. Well, it is the other dependent variable. Let's take that back, but it's a covariate here, so we use standard alpha level. So it gets a star, indicating that generalized anxiety did significantly adjust the means for test-specific anxiety. Test taker type, on the other hand, is sum square is 2.76, 1 degree of freedom, mean square of 2.76. F value is pretty small, 1.85 if you round it. And our sig is the one we evaluate using Bonferroni in this case, 0.025. And that is not only not less than 0.05, it's not less than 0.025 either, right? So this is indeed a case where we would not reject a null. We would say the groups did not differ on test taker. Our test taker types did not differ on test taking anxiety after adjusting for generalized anxiety. There's no difference between them. And our partial eta in this case, it turns out, is also correct. Our error comes from here. 85.20 is our sum of squares, 57 degrees of freedom, and our mean square is 1.50. In order to get our sum of squares total down here, you just got to add these things. So let's do that live. 45.50 plus 2.76 plus 85.20. I added these things right here. You get 133.46. And then for our degrees of freedom, I can do that one in my head. 57, 58, 59. That's our total degrees of freedom. So where do we get eta squared? Well, again, the easy way is right there. It's 0.03. The tougher way would be to divide the sum of squares for test taker type, which is 2.757, by the sum of test taker type plus error degrees of freedom. So sum these two right here. There's the formula. Sum of squares IV plus sum of squares error, that and that. And you divide this, the sum of squares for the IV, by the sum of these two things right here. Good Lord, that was confusing to even say. So I'm going to add this and add this to get the bottom of this equation. So 2.757 plus 85.203. I get 87.96. So someone remember that, 87.96. I'm going to divide 2.757 by, I totally forgot, 87.96, right? 87.96, I get 0.03. So that 0.03 is our eta squared. It also matches what they got here. All right, final questions. So using alpha 0.05, does the covariate, generalized anxiety, appear to account for a significant amount of variability in test-taking anxiety? Yes, it does. Why? Because the sig, or the F value here had a sig that was less than 0.05. That tells us generalized anxiety, it's the covariate, right? Significantly adjusted the means of test-specific anxiety. So second one, using our alpha Bonferroni, do the test-taking groups differ on test-taking anxiety after removing their differences in generalized anxiety? And the answer there is no, there's no difference. So our sig here was not less than 0.025. There was no significant difference between the test taker types, that is good and bad test takers, on test taking anxiety after you removed differences between those groups in generalized anxiety. So no, there is no significant difference. So does that support the researcher's hypothesis? Is it generalized anxiety or test-specific anxiety that best differentiates bad test takers from good test takers? Sure looks like it's generalized anxiety that's more important. Because why, when we account for this, we don't find a difference in their test-specific anxiety any longer. So, like if you're a therapist, suggests if you've got a patient who is having problems taking tests, you'd want to focus on their generalized anxiety more so than like test taking skills, right? You want to work on the generalized anxiety, that being anxious in general, take care of that, and it should, according to this study, fix the test taking anxiety as well. So go ahead and write your stuff up, and that's it for MANOVA. Actually, I take that back. One more thing. So on the write-up, the APA template for ANCOVA, just going back a week, people ask this. So I figure since I got your attention, let me help out. So let me get you guys the template for ANCOVA. APA, enter key. None of these is what I want, of course. Oh, that's because it's computational. Let me go back to week 2. So week 2, APA template for ANCOVA. Remember when you do ANCOVA, you have to include a plot in there that shows the covariate adjusted means and the unadjusted means, this plot right here. So note that neither the plot or the plot you get here doesn't have both sets of means in it. You need these means and you need these means in there. So in order to get this plot into your APA write-up, actually what you want to do is click on the outside of the plot that's in the template, right click, and go to edit data. And if you edit data, I can do it in mine in either Word or Excel. I'm just going to do it in Word. What you need to do is, instead of using a plot that comes out of SPSS, you want to use the plot. Where'd it go? Did it not work? Let's try that again. Edit, data, go. And today not working. All right, well, let's edit data. Let me try it one last time. And if it doesn't work, we'll do it. Let's just do it in Excel. Edit data in Excel. There we go. There we go. We're cooking with gas. So this is basically the numbers that are in the plot. So if we change these groups to bad test takers, good test takers, and put their unadjusted means, these guys right here, 11.6 and 10.50. And then we put their adjusted means in there, 11.28 and 10.82. And we close this, it will update this plot with the new numbers in there. So then you just got to like tweak things so that you've got a good y-axis, starts at 0, doesn't have too many values. It'll update these titles as well when you change them in there. And you just need to change the y-axis then to put, in this case, it would be test-specific anxiety, right? Mean test-specific anxiety. Anyway, that's how you do that. Hopefully that helps you guys this week. And that's that.